Hi all, good morning and welcome to today's webinar. I see we just have a few more people joining us here, so we'll give it another minute or so and we'll get kicked off then. Good morning everyone. You're very welcome to today's Northwest Chapter Ireland, Northwest Cyber Ireland chapter event. My name is Paul Brady. I'm a director on the Enterprise Information Security team at Optum and also one of the Northwest chapter leads. So to kick things off today, I just want to spend a few minutes on kind of why we launched the Cyber Ireland Northwest chapter in November 2020 and also talk about some of the progress we've made since then. So we started out with 4 chapter leads when we launched last year, including myself, Cian, John, and Veronica. We're also delighted to welcome Virginia from TCS and Jessica from Socorro to the group this year. When we launched last year, we decided to focus on 3 key themes. Those were networking and collaboration, talent and skills, awareness and advocacy. These lined up with the Cyber Ireland pillars, and we've been working hard since launch with other cluster organizations in the region and other regional chapters to develop the roadmap for the chapter in the Northwest here. So a roadmap was developed earlier this year, and we looked to be as kind of inclusive as we possibly could and consult other stakeholders and interested parties as we did that. So what have we been doing this year then? So on networking and collaboration, we all know there's been lots of webinars and virtual events over the last year. So we participated in a small number of them this year with the aim of doing more in this area and more face-to-face events next year, COVID permitting, obviously. We ran our own webinar in Q1 on cyber startups and scale-ups, and we were delighted to participate in the Atlantic conference in Q2, which was run by ITAG in Galway. So there's been a lot of work happening behind the scenes. On talent and skills, we participated as a chapter at the IT Sligo Engineering Expo earlier in the year. We also partnered with IT Sligo to organise a cybersecurity summer camp for transition year students. This had to be run fully virtually due to COVID and consisted of some instructor-led content Monday to Thursday and a fun capture the flag competition run by 0 days on the Friday. We were really blown away by the level of interest we had in the summer camp. We were limited to 25 places this year, but we could have easily filled 3 times that many. So we're hoping to build on that next year and obviously hoping to do it face-to-face in future. We've also been working with Hilary from the North-West Skills Forum and developing a cyber security skills audit for the Northwest. And we'll have Hilary join us here in a few minutes to provide some additional information on how you can get involved with that. In terms of awareness and advocacy, getting the chapter going has opened up opportunities to partner with other cluster organizations and to build up the cyber security network in the Northwest and nationally, which has been really positive for us. A reminder that the Cyber Ireland National Conference takes place on the 21st of October. We'll share a link to sign up after today's webinar, or you can find more information on the Cyber Ireland website. We had actually planned a face-to-face event in the Northwest following the conference, but unfortunately, due to the current restrictions, we've decided to postpone that maybe till later this year. So watch out for more on that. And just on the positives, I've kind of summarized some of them here and some of the highlights. So big thanks to the chapter leads and everyone else who supported the chapter. It's been great to see the collaboration and the level of interest in the topic, even though we've never been able to have a chapter meeting face-to-face, unfortunately. We've had so many great ideas come from the engagements we've had over the last year, but unfortunately, we haven't been able to take everything on, but hope to do more in future and continue to develop the chapter. Of course, all of this would not be possible without the support of the other Northwest chapter leads, the Northwest chapter members, the fantastic support we get from Owen and the team at Cyber Ireland. So I'm going to hand it over to Hilary McPartland here from the Northwest Skills Forum to talk to us about the Northwest Skills Audit and how you can get involved. So over to you, Hilary.
Thanks, Paul. So let me start by giving some background to how this project came about. For those of you that don't know, I'm the Regional Skills Manager for the Northwest covering Sligo, Leitrim and Donegal. So regional skills is part of the government's national skills strategy, and it provides an opportunity for employers and the education and training system to work together to meet the emerging skills needs of the regions. So what does that mean and what do we do? On a daily basis, we're meeting with companies in the region and assisting them in identifying their critical skills needs. So we offer free one-to-one advice on upskilling and training so companies can adapt or grow their business. So once skills needs have been identified, we link companies with the regional education and training providers that are best suited to their needs. So really what we're trying to do here is to help companies to capitalize on the full range of existing further and higher education supports that are already available at all levels, from entry level right up to executive level, because many of those are highly subsidized. But in the cases where we identify a skills gap that isn't been met, we work with industry and education to look at building new program solutions so that local talent supply is as well aligned to industry needs as possible. But in order for us to do that, we have to have a full picture of the skills needs in the region. So in the past, we have produced a number of skills audits in different sectors, for example, the ICT and fintech sector and the manufacturing sector. And actually on foot of the ICT and fintech skills audit, both Tech North-West and the Donegal ICT and fintech working groups were formed. So it just made sense for us to partner with the North-West chapter of Cyber Ireland on this skills audit. From my perspective, these skills audits are really valuable because I work with all the different education and training providers in the region. And that includes IT Sligo, Letterkenny IT, Donegal ETB, MSL ETB, and the various skills nets. So this will actually inform them about employer requirements in relation to recruitment and training and education. But it would also serve as a resource for organizations that are looking to hire or scale up their own cybersecurity teams. BoxD are the consulting partners on the project, and they have a wealth of experience in the cybersecurity skills area. So we're really delighted to have them on board. So what are we hoping to get from this report? We are looking to get an accurate picture of the cybersecurity activity in the Northwest so that we can identify potential areas for growth. We need to look at where there are significant mismatches in the demand and the supply of cyber skills in the region, because that will obviously inform future educational investment. We'd like to get a picture of the future cybersecurity requirements for the region. And we'll also be looking more generally at kind of challenges and opportunities. So no study is complete without a good old-fashioned SWOT analysis. And obviously with our location in the Northwest and the amount of labour mobility across the border, we'll be looking at the cross-border implications. But today is really all about asking for your support. We cannot do this study without your input. Over the coming weeks, we'll be reaching out to cybersecurity teams and organizations of all sizes in the region to ask them to participate in the research, either by telephone interview or online survey. So I am asking you to please provide your details via today's survey and we'll follow up with you. I think it's in all our best interest to try and maximize the cybersecurity employment opportunities in the region over the coming years. So please do get involved. Thanks very much.
Great, thanks, Hilary. And okay, so we'll have that survey at the end, as Hilary mentioned. So if you are interested in in supporting the skills audit, which is a great initiative, obviously you can provide your details there, and we'll be in touch. So on to our guest speaker today then. So Dominik is part of the Advanced Technology Collaborative team at Optum, and he is Vice President of Data Science. He's a technologist with an eye for innovation and a passion for artificial intelligence and data mining. His professional aims are to understand vertical business domains through the lens of data, improve data capture, write better algorithms, and ultimately deliver better products, generating meaningful and actionable insights. His work has previously featured in the popular media such as New York Times, Esquire, and Wired, as well as in academic fora such as scientific reports. So if you have any questions for Dominik or the team here as we go through the presentation today, please feel free to use the Q&A function, and we'll keep an eye on it throughout the presentation. So Dominik, I'll hand it over to you here.
Hello, everybody. I hope you can hear me. I'll just start my screen share. Oh, Paul, I think you need to unshare. Stop sharing. Okay, thank you. I'll go in. Just 1 second. I have too many screens open, too many windows open. I can't find my, here we go. Share this. Okay. Thumbs up for who can see me, or better, the presentation.
We can see you, Dominik, yeah.
Excellent. Okay, thank you so much, Paul, for the introduction, and also thank you for the chapter leads for inviting me. Just by way of introduction, how I got actually into this, I'm not an expert in cybersecurity, I should say that, but I really follow, I try to follow the trends in artificial intelligence, and in about 7 years ago, sort of a shift happened in the AI community where a really novel trend was introduced to ultimately break deep neural networks. Adversarial AI itself is actually not that new. If you think about game playing AI of the olden age, even where you can reason over what the current state is, let's say tic-tac-toe, you actually also use adversarial AI to understand what your opponent is likely going to do next, right? We know the opponent is trying to win a game. So adversarial AI is, of course, not new. But about 7 years ago, with the advent of deep neural networks and how you can fool deep neural networks, really novel opportunities opened up. Initially, they were harmless in the sense that they improved robustness of the deep learning network. But also, what is important to keep in mind is that AI technologies are dual use. So they can also be used to break things intentionally. So this is what I'm going to cover today. So I had the introduction through Paul, so thanks for that. I included some coordinates. You're welcome to reach out to me if you have any questions after this. Let me move one screen and minimize this here. Okay. So let me start with this following statement. The proliferation of AI systems will lead to changes in the landscape of threats. I think this we already see this actually. So in that sense, it is not a novel statement for experts in cybersecurity. But let's uncover a little bit what we are about to see, or what we are seeing increasingly. For me, the objective of this talk is provide an overview of potentially altered threat landscape. So that is the zoom out perspective. I'd like to zoom in a little bit and introduce high-level mechanisms of attacks against digital security. I've given a number of talks on adversarial AI where I put my hacker hat on, and I wanted the students to understand how you can actually play with mathematics to fool a deep neural network, for example. So I'll uncover a little bit the mechanisms of this today. I'm not going into technical details, but keep in mind the technical detail is really, really interesting in its own right. And then, of course, a call to action. And hopefully that resonates with this chapter as well, especially in what Paul called out a few minutes ago. All right, so what can we expect? So I think we can expect, and it's I took some of this content also from a report that I referenced at the very end. Expansion of existing threats, introducing of new threats. So now that we have more and more AI deployed in enterprises, we will see now ways of attacking those and fooling those. The change of typical character of threats will also be prominent. And the three security domains, digital, physical, and political security, we will also be impacted, of course. I'm focusing mostly today on the digital, physical security aspects, with an emphasis on digital, actually. Let's look at a few examples. So poisoning attacks through adversarial examples. So can you introduce into the machine learning training process examples that are minutely changed or have invisible features that trigger a false response or a faulty or a fooled response. So sometimes this is very, very hard to trace. Once introduced into the system, it's very hard to remove. Exploit human vulnerabilities through speech synthesis and fake images. We've seen plenty of those actually in social media, and often these are actually used for persuasion tasks, targeted propaganda or deception, manipulated videos, for example. And the increased scale and efficiency of artificial intelligence specifically can lead to an increase in spear phishing attacks. These are usually very heavy in manual labor. There's a lot of creativity and a lot of digging and research that goes into it, and it takes quite some time to hone in on a target and launch the spear phishing attacks. But with AI, these things can potentially be automated. One thing I could say is if you can read, like if you got access to somebody's email account and you can read the emails, you can train a neural network that might pick up the sentiment of interactions between the account that you hacked into. So you might be able to generate a message that will trigger a positive response from the account holder. So these kind of things can be done. Subvert cyber physical systems. That's also quite popular now in terms of popular media, causing autonomous vehicles to crash. And we see a couple of examples later as well, and how that looks. But what I would like to emphasize as well is how are high-level enterprise architectures going to look like in the face of attacks. So let's take a few steps back. It doesn't need to be AI ultimately that I'm trying to attack, right? So it could be a business process that is rules-driven, or could be even a business process that is human-driven. What attackers can do with AI is they can learn a meta model interactively. So if I can query the business process, i.e., I can send data and I can receive an outcome. If I can do that, even as a normal interaction, I can steal ultimately the underlying function logic of that business process and build it into a meta model, right? So once I have a meta model, I can find adversarial data. I can find adversarial examples given that meta model that I'm using as a proxy to the business process. I can now launch adversarial examples, derive adversarial examples, and submit the attack vector into the business process. And the business process very likely is going to respond as expected. Might fail as well, but the meta model can continuously learn how the business process reacts to faulty data or adversarial data. So this is the automation that can happen at the most basic level. There are a couple of, let's say, offshoots of this. So let's look at how enterprise architectures try to tackle or deploy AI. Usually a business process might be quite expensive. So it is in the interest of the enterprise to remove friction or cost from the business process. And what do enterprises do? Well, they build machine learning models that represent this business process. Usually there's data behind it, right? So now we have a machine learning model that is being exposed, And now imagine that this machine learning model is image-based, and let's say that machine learning model is even known, like Google, for example, uses image models that are exposed to their cloud APIs that are well published. So if such a model is well published, I can learn directly of that published model an adversarial attack. Derive adversarial examples from a known model, and then I can submit the attack vector. What is interesting now, what starts off as an evasion attack actually indirectly turns into a poison attack, because what happens now underneath, I send adversarial data to a model. Let's say that model responded as the attacker intended. Now that interaction is stored in a historic database of data. For now, the enterprise doesn't know whether there was an attack launched, but the data, the interaction data, will be part of the training process once the model is being retrained. And now something really interesting happens. If the evasion attack was successful, it slowly but surely undermines the model, because we need to keep, enterprises need to keep the models up to date, so they need to retrain from time to time. And these attacks that were successful will now be reinforced. And that reinforcement ultimately has the effect that attackers will find it easier over time to launch the attack, unless they get noticed, of course. Okay. So now let's look at a third iteration of this. So we again have a business process that is being modeled within the enterprise boundaries. And I don't have access to that model. It's not a public image model, let's say. It is something that is private to the enterprise, proprietary. So I can again, through regular interactions with that machine learning model, with that exposed service, I can build a meta model. In fact, it doesn't even need to start off as somebody with an adversarial mindset. It can just be, I could be a huge customer to that enterprise, and I just want to make my own interaction with that enterprise more efficient. So I can build that meta model. And again, the same thing can happen. I learn a meta model interactively. I launch an evasion attack by deriving adversarial examples from a meta model. I submit the attack vector to the model. And again, I have the same effect that indirectly I poison the machine learning model by introducing these successful adversarial attacks into the training set. So now we have had 3 iterations of how high-level enterprise architectures might look like. So it's important to keep that in mind, because when we look at fooling machine learning models, we often think about white box attacks, like I have access to the actual model. Here I'm arguing that you of course have an easier play if you do have access to the actual model. But if you don't have access to it, you might only have access to the black box model. You can build meta models almost as efficiently, actually. Okay, so let's make another more machine learning statement to think about how we think about machine learning models as classification networks. So given a classification neural network, I have a hypothesis function. The X might be an image. I get as an outcome a Y, and that Y might be what does the image entail? Is it a dog, a cat, right? So it is very easy to find an X hat, so a small, minute change of that image that's virtually identical, possibly even not noticeable to the human eye, that identical to the original image, such that I can fool the neural network to deliver a different response, a different Y. So it could be just anything else. So I could say I modify an image with a dog in it, and the deep neural network now should respond with anything but the dog. It can also be targeted, of course, where I can say, hey, respond with a spoon. So this can be done using machine learning. Let's look at a couple of examples, what that minute change might look like. Actually, the first time I came across this, this paper is relatively new, actually, it's 3 years old. Single pixel attacks. So we have, I think it's 32 by 32 pixel images here, and top left you see an airplane. And by changing a single pixel, I can now force the neural network to recognize a dog instead of the airplane. The next image is a car, and I can force that car to be misclassified as a dog again, and so on. And that actually really, really surprised me, because now if a single pixel can alter the output of a deep neural network, what could these single pixels represent? There could be a speck on the camera. There could be some small fault on the sensory, on the sensors of the camera, right? So who's to say that some of these faults cannot occur in real life and are unintentional? So this is quite surprising, I found initially, but in fact, mathematically, it's very, very easy to launch these attacks, single pixel attacks. Here's something that is from the physical domain. We have a stop sign, and now we put post-its or stickers on that stop sign. And from many angles and zoom levels, this stop sign is now classified not as a stop sign, but as a speed limit sign. And in the bottom row, you see graffiti on it. You see love, hate written on that stop sign, right? And again, from many angles and zoom levels, this stop sign at the bottom is again classified as a speed sign, speed limit sign. So naturally, the autonomous vehicle use case comes to mind, right? If I can alter the physical appearance of road signs and make autonomous vehicles misbehave, that is of course a huge threat. And I don't even tamper with the car itself, right? Okay, moving on. Here's another one that's a bit tongue-in-cheek, the elephant in the room. It's back to the digital security flaws that we might observe. You see a fairly busy living room with a person sitting on a chair. Once I put the elephant in the room, so on the left-hand side you have the original image, and you see a couple of frames drawn onto it, and these frames indicate objects that have been identified by a machine learning algorithm. It's barely noticeable, but there is on top of the person's head a small elephant, kind of a patch introduced into the image, superimposed. And now I can see, looking carefully, it's a little bit difficult to see. I can now see that some of the objects are misclassified only by introducing an unusual element in the picture. And that is also quite surprising, because now the deep learning algorithm doesn't only introduce, it's not only locally sensitive, it's globally sensitive to what is in that picture. Anything that is unusual and is placed somewhere in the picture can trigger a misclassification. So that's also quite surprising, actually, because naturally you would say if the patch is, let's say, at the top left corner of the image, something that is at the bottom right or at the opposite ends of the image shouldn't be misclassified. But in fact, it does happen. So how do we fool the classifier? So let me go through some drawings, schematic drawings about a potential use case to classify chest x-rays into tumor, pneumonia, or no finding whatsoever. So on the left-hand side, we have data. It's going into a neural network model depicted in the middle. And often these models are very deep, so they are not only one hidden layer. And then we have a prediction. So one of the three that I've illustrated here: tumor, pneumonia, or no finding. I can now introduce constraints. I can say I would like to minimize input changes in order to force the prediction to be different. So I can force a prediction from tumor to no finding at all. These two constraints can be combined mathematically. Or alternatively, let's remove the minimizing aspect of the image. I can just say, maximize the classification error. I would like the tumor to be not to be recognized anymore, and I would like to make the biggest error possible. And then I would like to combine these two approaches. Let's say the two constraints. I would like to maximize the classification error and minimize the changes to be made to the data. So here's the only equation that I will show. Okay, it's not too important to really try to understand it, but what I want to illustrate is that these things have a mathematical problem setting and they have a mathematical solution. And oftentimes they can be solved with a solver that already exists. So there's fairly little mathematically to do except to set up this problem. So what am I saying? I'm trying to minimize the changes in the input. So that's the first line. So I'm minimizing the change that I introduce to an image, for example. And then such that illustrates two constraints. One is I would like to introduce a target. So I would like the image to be classified as something else. And then it would originally be classified as. And then the second constraint is the perturbations should be valid. So of course I can't just add any number to the pixels. They need to be minute, they need to be small, and they need to be within the RGB range. So we kind of need to introduce that constraint as well. And what to me and to the authors of that paper that I mentioned earlier from 2014 found really surprising is that, and that's a bit nuanced now, even though we are using gradient information from the model, so we want to maximize the error, right? So we are using the gradient information of that particular model, so we see inside the model. The perturbations that we are introducing are not random artifacts of the learning process. So let me pass this. Adversarial examples produced using one model transfer to other models. And that to me is mind-blowing. In fact, it is really disappointing from the cybersecurity perspective, because what that ultimately means is I can use one model architecture to derive adversarial examples, and I can use a different model architecture to, let's say, classify the same thing, to still fool the classification. And that is really, really hard to comprehend in some sense. And from a hacker's point of view, it's a great opportunity. And from a cybersecurity perspective, this is going to be hard to solve. Like, what do we do? Okay. How do we target an attack? I'm not going to go into this actually. Sorry, I forgot that slide. But applications in healthcare, I want to give a few more examples that are something I deal with more on a day-to-day basis. Again, this is published material from 2019. A set of researchers from MIT and I think Harvard as well published the following adversarial attacks on medical images in science. On the left-hand side, you see the original image, and the original image depicts a skin lesion. It could be taken with a mobile phone or with a professional camera. Now we introduce adversarial noise. So this is what you often see. It's not a single pixel. You introduce a noise mask that you dial down. So that's the factor 0.04. You kind of multiply this noise mask with a very, very, very small factor, and you overlay this adversarial noise mask to the original image. And that's what you see on the right-hand side. To you, as a human, to me, there's no visible difference. However, while the original image was classified as a benign lesion, the right-hand side gets classified as malignant. So this is, again, a quite surprising artifact. Or I could use a different perturbation. So instead of adding this noise mask, I could rotate the image a little bit, just ever so slightly until it starts beginning misbehaving. And this is also something that is fairly easy to do. So you see here the craft in finding these attack vectors is actually, what do we do? Is there domain expertise that I can exploit, or are there nuances in how the data is represented that I can exploit. So the crafty aspect here is really coming up with these perturbations. The math behind finding these adversarials is fairly straightforward, actually. Here's another example on medical records. So we focused previously on images, but now you can also do the same with text. So on the left-hand side, you have the text, I read it out. The patient has a history of back pain and chronic alcohol abuse, and more recently has been seen in several, and so on. So here we might have a classifier that highlights that the opioid abuse risk might potentially be high. So what could we do? So if I were to submit, let's say, an electronic medical record to an insurance company or something like this, or there may be other use cases within the hospital, I could now think of adversarial text substitution. And these are not random, right? So now the patient has a history of lumbago and chronic alcohol dependence, and more recently has been seen in several, and so on. So here, the replacement, so the blue underlined font there, the blue colored font, highlights a related medical concept that has been replaced. So lumbago with back pain, and instead of alcohol abuse, we write alcohol dependence. And now the opioid risk is low, purely by the choice of language. The semantics is exactly the same. And let me highlight this creative aspect. We talked previously about meta models, right? So you can build now, you can build a semantic relationship between words, medical concepts, say, and if you realize you would like to find an adversarial example, or you would like to trigger a different response from a classifier, you can query the semantic relationships and find out whether any related words, related word substitutions would yield a different outcome. So again, let's say to the enterprise, that might actually appear harmless, because the enterprise doesn't necessarily know that you're being creative here and trying to find a different classification outcome. So there's a certain gray zone. The bottom example is in a reimbursement scenario. So we have ICD codes. So these are disease codes, international classification codes of diseases and symptoms of diseases. They are coded up for billing purposes on health insurance claims. So the hospital does it, and the health insurance will need to look at these coded claims and pay appropriately, reimburse. So now 277.7 metabolic syndrome has been coded up, and the reimbursement is denied. Now with adversarial coding, again, it's the same situation as above. We use something that's semantically similar, maybe in parts more specific to the metabolic syndrome. We now replace the single code with 3 codes, and very suddenly the reimbursement gets approved. So this is the coding effort that goes into submitting a claim. And again, it could be not even an adversarial. It might just be an okay thing to do in the gray zone of submitting a claim. Okay, so if we know how to attack, can we easily defend against those adversaries? So that is, of course, a big ticket item, right? So let me go through not the technical aspect of it, but more high-level recommendations, and that might resonate with you as well, and especially what Paul said at the introduction. Collaboration. So policymakers should collaborate closely with technical research to investigate, prevent, and mitigate potential malicious uses of AI. Naturally, and the domain experts and how you deal with potential adversarial attacks do require policymakers' input, as well as the technical researchers' input. The dual use aspect I mentioned earlier, which is true for pretty much all AI. I can use it for harmful applications, but also, of course, for benevolent ones. So researchers and engineers need to proactively reach out to relevant actors when harmful applications are foreseeable. The cybersecurity domain has actually protocols around this as well, and best practices. What follows: identify best practice for addressing dual use concerns such as computer security, right? And cross-functional recommendations are also important. Seek to expand the range of stakeholders and domain experts involved in discussions of these challenges. If the technical exposure of this material stays within the technical domain, it is very hard to escape and draw in the right experts to make meaningful impact. So how do we create robust and secure AI? We can, on an enterprise, so think about an enterprise architecture now, we can introduce rate limitation, limit the set of inputs a single user can submit to a system. That might be a relatively weak deterrent, but effective. However, any, let's say, public API or any service that is exposed publicly and it's data driven, I feed input into that service and I get some output out of that service, let's say a claim got approved or not, ultimately offers the opportunity for hackers to build meta models, and they might be not really visible. So there has been in AI, there's a long history of active learning. So how do you minimize the queries to a system in order to learn a meta model? So that is, of course, an active research area that is very common for, let's say, design of aerospaces and things like that, that are very, very expensive. However, the same AI can of course be used to build meta models. So rate limitation might be a deterrent, but we need to keep in mind that there is also the counter argument that AI does look into opportunities and mechanisms to learn meta models with minimal interaction. Input validation is also very effective. Focus on permissible submissions to your AI models. That is also very common in defensive programming, right? So you're bounding what you expect into your APIs, right? So that shouldn't be different in AI models. Robust model structuring. Structure your AI models in order to offer natural resistance. I'll go into a little bit of detail in the following slide. And adversarial training. So introducing adversarial examples in your training process is also really helpful. Let's cover this a little bit more in detail. Robust model structuring can mean consider building Bayesian deep learning models. For those who are more at home with statistics, Bayesian deep learning models they do not make point predictions. They ultimately make predictions on a distribution, build a posterior distribution. So often those are more difficult to attack. Or build machine learning models that can also express I do not know. So oftentimes you see machine learning models that say, is it a cat or is it a dog? And if you only have these two options, if you put in a rat, well, the classification is now going to force either a cat or a dog. So introducing I do not know might actually help as well to be able to say, hey, I don't know whether this is a cat or dog. It seems not easy to identify for the machine learning model. And of course, there are libraries like Clever Hunts to identify vulnerabilities of ML models. IBM have their own toolkit as well to identify vulnerabilities. And ultimately, deep learning are supersized models that have many millions, hundreds of millions, some nowadays even billions of parameters that are being tuned. These supersized models offer plenty of opportunities to attack. So we can prune them potentially. So how can we remove, let's say, 10% or 90% of these parameters with minimal loss in accuracy? So that can also mean robust model restructuring. So adversarial training, I just mentioned it earlier as well, is a very easy way to add defense mechanisms to machine learning training. And that's what the original authors of the 2015 paper that I cited below have done. However, it's it's kind of like a game of whack-a-mole, right? So adversarial examples are produced using very particular attack vectors. So I'm exploiting certain attack vectors. For example, I'm rotating. If I now introduce rotation examples into my training process, I will be able to defend against rotation attacks. However, if I now introduce noise, like pixelated noise, I'm not necessarily defending against those. So if I know the attack vector, I can introduce these adversarial attack examples to the training process. So that's very typical in the cybersecurity community. You're always one step behind attackers potentially. But this adversarial training is also somewhat brute force, because I'm brute force generating a whole lot of adversarial attacks, potential attacks, and guarding against those. So let's cover up in the last few minutes what we've learned. So adversarial impressions are constructed using optimization formulations. So what's important to note here, these optimization formulations are often black box. So they don't, I can use off-the-shelf tools, mathematical tools to arrive at adversarial impressions. So that's important to keep in mind, that the barrier of entry for attackers gets lower and lower. It's a super active research field. Over a dozen of papers a year at each major AI conferences deal with adversarial attacks nowadays. The fundamental mechanics can be surprisingly simple. And that is also something that is important to keep in mind, because again, it lowers the level of entry for attackers. The art is often in the perturbation function. So do I rotate, do I add noise, or is there anything else I do to the original data in order to craft adversarial examples? And we showed that adversarial examples impact autonomous vehicles and healthcare and many, many other domains. Social media, we have very, very good examples there as well, especially to polarize populations and things like that. So what we learned from with regards to defense mechanisms, AI algorithms can fail in really surprising and unintended ways. AI safety is promoted by considering adversarial examples. We can also look at formal worst-case verification techniques. However, these kind of formal techniques are very common in software systems, traditional software systems. These theoretical tools, however, don't guarantee against adversarial attacks. So we still don't have a formal mechanism to verify against potential attack vectors. So there's a lot of research going into this, but that is also because AI looks very different to traditional software, right? And all recent defense mechanisms, and this is also a little bit of a downer, if you want to put it this way from a cybersecurity perspective, all recent defense mechanisms can be broken. And there's a really, really good paper by Nicolas Carlini from Google on adaptive attacks to adversarial example defenses, where he launches adversarial attacks against all recently published defense mechanisms. And it takes relatively little effort to break those. So here I want to highlight one last thing. I dug it out yesterday from the US Bureau of Labor Statistics, and it shows the 20 fastest growing jobs over the next decade. I cut out the declining jobs, they're not so interesting. So on the y-axis, you see the employment change over the next 10 years. On the x-axis, you see the median annual wage. And what I really want to highlight, the orange bubbles in the domain of computer and mathematics. The biggest one of those is information security. And we can expect that information security over the next decade is going to increase by 30% in employment change. So naturally, there is a lot of demand in this area. And also, since it's fairly far on the right-hand side, the salaries are pretty good as well in that space. I don't know, I didn't have a similar picture for Europe, but it highlights a kind of a trend. So the proliferation of AI really does change the threat landscape, there is going to be a lot of work to do to defend against potential adversaries and be ahead of the game, if possible. I stop here, and I have a couple of minutes. I hope I try to squeeze it in. I'm 1 minute late, so thank you very much.
Dominik, really interesting presentation there. I see we've one question here in the chat just in relation to the kind of machine learning training sets, and that is there an imperative that the ML training sets are controlled and protected?
Say it again, what is the question?
Yeah, so is there an imperative that the machine learning training sets are controlled and protected?
That's a good question, right? So I talked about how one can poison the training set, right? Let's assume for a moment that you're exposing an image classifier, right? This image classifier collects the images that are being put in, and it produces the output, right? So you're logging ultimately, here's an image and here's the output that this classifier produced. You don't necessarily, at this point in time, you don't necessarily know who sent the image. Was it altered in any way, right? And because you want to improve your service over time, what very easily happens is that you expand your training set over time, make it bigger and better. We are in the big data world, right? So more data means better machine learning algorithms. However, if adversarial attacks come into your training set this way, and you don't have a mechanism to identify whether this is a valid image or not, you're ultimately introducing these images. And I'm not sure whether audits are going to solve it, because ultimately you have a lot of data, a lot of interactions going, right? So can you audit every single image? Remember that, let's say the visual inspection is very labor intensive, right? And humans make errors too in classification. So I'm not entirely sure how we do that, right? But there's certainly something to be said about the quality of the data, right? So it's input validation, I mentioned that, but it might also be a post, once you've collected the data, once you've validated, maybe there is a post process that still is going to look at the data to certify it to some degree. But I'm kind of reminded by what Stephen Hawking did to black holes. Like he several decades ago, he said black holes are only ever going to grow; they're never going to shrink. And I almost feel like right now that's pretty much the same for these attack vectors, right? If initially you put a machine learning model out there that doesn't contain any adversarial examples, and you find it hard to identify adversarial examples, you're ultimately growing the gray space. You're growing the adversarial space as well, so that the machine learning model will permit more and more of these adversarial attacks. And that's why I think it is so important to continue on this agenda to identify technical mechanisms, but also domain experts, like whether it's from the medical domain or speech domain or any other domain, right? They need to work closely together to identify and certify, let's say, the data that goes into your machine learning models. There's one saying, garbage in, garbage out, right? So if you don't know you have garbage in your data, you ultimately will over time produce garbage. And this is very, very subtle. Very challenging problem. Yeah.
Just I think we have another couple of questions here in the QA, but what I might do just before we wrap up here is just ask Fiona to kick off the survey, so that we can just gather, if anybody's interested in participating in the skills audit, we'll just gather some info from me via the survey here. I'm not going to pretend to understand this question, Dominik, but I'll read it out anyway. Is there a trade-off limit between pruning supersized models and keeping enough parameters or aspects to get useful results?
Yes. So let's say you have one of those billion parameter models, and let's say in your particular use case, you have to put it simply, let's say you have 95% accuracy. Let's say it's a balanced data set, so we use accuracy as a metric. Now, once you've trained it, now there are very targeted pruning techniques that take out most of the parameters that don't contribute to producing a response. And as you do that, your accuracy will naturally drop. It doesn't improve, right? The accuracy is not going to improve by taking out parameters. So ever so slightly, they're going to drop. You kind of stop at a level when you think the curve, the decrease in accuracy curve, kind of starts accelerating. So yes, there is a trade-off, and you start with taking 5% parameters out at a time, or even less, and you observe the curve, and you can stop at a moment in time when you kind of say, hey, I'm not happy with an accuracy below, let's say 93%. So that's what you do. So that is ultimately the trade-off.
Yeah, thanks. Just one more question then, and we'll wrap it up at that. So any thoughts on attacks on bot technology, I presume that's chatbot technology deployed by many service providers across the web?
Oh, there's a very good example, right? Tay, Microsoft Tay was a chatbot that ultimately was an experiment. That chatbot was put out, announced on Twitter, and it resulted in a lot of interactions with that chatbot. But what the audience, or what people noticed fairly quickly, that Tay can be tricked into racist slur language, Microsoft, within 18 minutes, I think, of putting Tay out there, had to shut the service down because Tay turned out to be a racist, right? But Tay was tricked into this, right, by interacting, right? So Tay responded, engaged with the audience, right? So somehow it learned to be that racist dialogue partner, and that is of course one of the really negative examples. I think that's also one of the reasons why a lot of chatbot technology is scripted, right? You can't oftentimes trick it really into these kind of racist languages, because it needs to find certain action points or information contexts that you would like to resolve with a chatbot. So let's say if you call a customer service, or if you have a customer service chatbot, right? If you were to insult that chatbot, they're not going to respond in kind, because that insult is not scripted. But that makes also chatbots a little bit difficult still, right? So that scripting takes also time.
Yeah. Okay, great stuff, Dominik. Listen, thanks again for coming along and giving us some great insights there. I think a lot to think about. So just to wrap up here then, just with a quick reminder then that the Cyber Ireland conference I mentioned takes place on the 21st of October. I see we've got the link here in the chat. We are planning to host a face-to-face event later this year. So, the best way to kind of keep up to date is through our newsletter, or keep an eye on the Cyber Ireland website or social media channels. So again, a big thanks to our guest speaker today, Dominik. Also thanks to Hilary for coming along and supporting the event today. I understand the survey is going to go out when we wrap up here. So if anybody is interested in supporting that skills audit, please feel free to send us on your details there, and we'll be in touch. So look, thanks again, everybody. Great to be back today with a webinar, and we'll talk soon. Thank you.
Thank you all. Bye.